But Horton equation really didn't account for the actual processes. It is just empirical equations. It doesn't really relate to a lot of those processes that I identified before. For instance, the initial moisture content. For instance, the soil type. It really doesn't have a very specific type of fundamental properties associated with these equations. That's why there is another equation. It's called Green-Amp equations, which relate everything to that actual physical properties. So this is not empirical equations. So what you see over here, F is infiltrations. Infiltration depends on saturated hydraulic conductivity, or Ks. So you can, if you write this equation, it will be Ks plus Ks time a factor. And that factor is this term over here, okay? Which is what I explained before. You know that the infiltration is a function of the difference in moisture content before and after the rainfall, when it was dry versus what's the maximum capacity. So this is the theta s by theta I is the moisture content difference between saturation and the initial moisture content. Then capillary suction. This is a function of what's the particle size, what's the pressure by which you can pull that water inside the soil. So these are all related a physical quantity that we can relate to. And F is the amount of rainwater already filled into the pores. That means this is that capacity has already reached. So you will not be able to, they will not be able to participate in receiving more rainfall, rainwater. So this is the equations. And if you see what is the infiltration rate, all you have to do is, this is infiltration rate, F is infiltration rate, and then F dt, if you integrate that, you should be able to receive complete amount of water that infiltrated into ground. So if you do integration, you receive F, and that integration term will be this. And this is a circular problem. The reason is infiltration rate or total amount of water that received at any time is a function of what was the infiltration capacity before that time step. So this is an iteration step. You'll make a choice of F, calculate Fn plus 1, then you substitute again back there, and then it will until it will converging. So this equation you cannot solve by calculator. You have to use a kind of a numerical value or do multiple time step. So I'm not going to solve this equation, just know that this exists. I'll not ask this question in exams, but this question is solved in one of those handouts. So in any case, if it is needed for your project, you will be using these equations to estimate the infiltration rate. But just know as a concept. Again, for this thing, you need to know this suction coefficient and saturation, all these factors. And those constants are already given for you in this table. So for different soil type, you have porosity, which is related to saturation, complete saturation, theta s, because that's the amount of water that you can fill in. And then it's also related to, this is capillary. And then also this is hydraulic conductivity, or K saturated. All these numbers are given. So if imagine you have a site and you know the soil type, you'll go back to this table and you'll be able to find the infiltration rate at different time. Any question?
Yeah, I had a question really quick.
Yeah.
So the green amount equation is better than the Horton equation just because it uses measurable values, right? It's something that you would use in the field instead of a theoretical equation.
Correct. So the reason the other equation is not easy to use is because you have to determine that empirical parameter for your site. But sometimes it's useful when you don't, if you have a very heterogeneous site, you have different types of soil, different types of materials, and different structure. That's very hard to use a concept, something like green amp equations, because There are multiple different type of case. There are multiple types of parameter. Then the best bet is to use something like empirical equations. Then you don't have to worry about individual soil type.
So for our project, if we wanted to use the green amount equation because it had multiple soil types, could we run that model multiple times and then take the average of it if we wanted to do the average for our site?
Well, I think this infiltration rate is not. You have to think of how this is related to your site. For instance, are the soil are all mixed in one location? Then you can pick one values. Or if there is one location with a different soil and then other side of the other site in that other part of the property has a different soil, then you have to maybe do different way, like how you said.
Okay, thank you.
Great. So again, this is the summary. What you learned so far is topography. This is not sloppy. All I try to say is that if the slope is high, your infiltration rate will decrease, because if it is slope, most of them will become runoff. Runoff also depends on, or infiltration rate depends on geology or soil type. If you have soil is sandy soil, you have more infiltrations. If you have clay soil, you have less infiltrations. Same thing, you can think of runoff is inversely proportional to infiltrations. If you have more infiltrations, you have less runoff. Vegetation cover or land use type. If you have impervious surface, you have more runoff, less infiltrations. Hydrometeorology, it's all about coastal area versus desert versus mountain. The reason is this is related to what's the initial moisture content. If you think of mountain, the moisture level will be very different, the soil heterogeneity will be different, so the initial moisture content will be very different from other areas. And then finally is what kind of rainfall received in that area. So next couple of slides, what we'll learn about is how to actually define the rainfall, how to quantify the rainfall. Any questions so far? Because so rainfall characteristic, think of rainfall. Anytime you say rainfall, how do you identify them? If you see, in news channel, you'll see that somebody says we have 2-inch rainfall or 1-inch rainfall, or some 2 mm rainfall. They describe rainfall as a length scale. The reason they describe that is all about this. Imagine this is area, and it says 2-inch rainfall. All it means that it assumes that if the rainfall amount, if you pour entire water on the entire landscape, it will create a ponding with 2-inch as a height. So this is the 2 mm rainfall. That means you have water filled with a bucket with the area of the same area, about 2 mm height. And when you think of, that's the depth, rainfall depth, okay, or the amount. So rainfall depth can be always converted to total amount of rainfall just by multiplying the area of that catchment, that locations. So this is depth. So area times depth of rainfall would be volume of rainfall. And this is catchment area. That's the location. The assumption here is that the entire area receives the exact same amount of rainfall, which is not correct, but that's the assumption you have to make for this kind of model. There are other models that account for different heterogeneity. We'll get to that. But this is a concept. Depth and volume are very similar. The only difference is you divide by area. Then also you talk about rainfall intensity. The reason is when I talk about rainfall intensity, now we talk about heterogeneity in terms of time. Because when you think of rainfall, the intensity of rainfall is not same throughout the different time. For instance, if it rains for 2 hours, you may receive very small amount of rainfall initially, then it suddenly increase very high, and then it slow down with time. So that rainfall intensity means amount of rainfall received per unit time. So depth versus time is rainfall intensity. And that rainfall intensity could vary with time. Okay, and typically the rainfall intensity is described per hour or per day um, when it comes to the natural convention. So we have, and then also we have duration, how long it rainfall happens. So we have four quantity: rainfall durations, rainfall intensity, rainfall depth. Intensity and depth are kind of similar, because if you know the time, you can calculate that. And then also rainfall volume. Rarely we mention rainfall volume. Rainfall volume is calculated at the end based on all those other factors. So these are the rainfall event characterizations. But what about when you try to compare rainfall events in different time of the year? So then we call about rainfall frequency, means how often it rains in that location, and how often a certain type of rainfall happens in that locations. So that we call return period, or the probability of having a rainfall to occur in that location with certain intensity. So that return period is important, because when you think of green infrastructure, you are going to design for green infrastructure such a way that it can handle water received during a heavy rainfall or very worst case scenario. So that means you should look for how often that worst case scenario would occur in that areas. For instance, a lot of times you can say this area receive high flooding because it receive rainfall every 100-year storm. It means that, doesn't mean that this rainfall happened 100 years before now. All it means that the type of rainfall you receive in that area, in that location which cause flooding, most likely it comes every once in a 100 year. Means the return period is, this is on average, it's a statistical term. So again, these are the terms you are going to come across in many locations or many times. And this is just example to show that how we can calculate return period or recurrence based on probability. So the example is, what is the recurrence interval for a storm event that has a 20% probability of being equal or exceeded within a given year? So the probability is given is 20%, which is 0.2. And I ask you, and it says within a given year. So that's the time here is a year. The time term is year term. Within a year, the probability of having that rainfall is 20%. So then I ask, what is the recurrence interval? How likely this rainfall occur? What's the time returning period? Again, returning period is 1 over probability. So this is per year. That's why it's written. So that will be 0.2 year. So this is 5 years. So the return period is 5 years. Means that every 5 years, this kind of rainfall intensity might happens in that area. Same thing for probability of 2%, which is 0.02. Return period will be 1 over 0.02, which is 50 years. Okay. So again, this is just a simple math. Now this is the last example we'll do. This is the typical rainfall data you'll receive. It means that at different time, so this, all it says is what type of rainfall amount received in a particular area in last 100 years. So this is yearly average. Okay. So if you see over here, this is the rainfall depth, the y-axis. This is the time of the year. And it says, if I ask you to calculate what is the intensity of a 100-year storm event at these locations, what it means, I ask you, in 100 years, storm event means you must have a rainfall that only happens once in 100 years. So if you see, if you draw a line over here, only one rainfall that goes beyond that one. And that's the one happened once in 100 years. And the intensity over here is 6.5 inch. So that means what is the intensity of the 100-year storm event? Then you write 6.5 inch. what is the return period for 4-inch 24-hour storm event? Again, these are 24-hour storm events. So I ask you, what is the return period? If you see at 4-inch, if I draw a line here, you find that 1, 2, and third, 3. 3 rainfall happens in 100 years that exceed that 4-inch rainfall. So the return period is, in 100 years, you have 3 rainfall, 3 occurrence. So that means the return period will be 100 over 3. So which will be, oh no, actually this is another one here, 4. So that means 25 years. So what you are saying here is that in 25 years, at least you have one rainfall, which will be either 4-inch or larger than 4-inch of rainfall. Then if I ask you question, how does return period change with decreases in intensity or rainfall? It is written a little bit weird way. What I'm saying is, if I ask you what is the return period of a smaller rainfall intensity, is this going to be smaller or larger? The answer will be smaller. That means if you have 1-inch rainfall, there is more probability of having a 1-inch rainfall within a certain time than having a 10-inch rainfall, because as heavy rainfall doesn't occur very easily. It's not common. So that's it in terms of the what's the on average how you can calculate rainfall intensity. So rest of the slides I'll record it and share with the class. But before we